Okay, welcome back to the second lecture. The end effector, as we can see, consists of three rotational movements, theta 4, theta 5, and theta 6, pitch, yaw, and roll. And then, of course, in the virtual center of this end effector, you see the three unit vectors, N, S, and A. A is the approach angle of the end effector, going straight up. Okay. And then S is perpendicular to the blades or to the fingers of the, and then N is the third one, which is going through basically right-hand rule. If you have, for example, A cross product with S, you get N. Okay. So, in general, this transformation at that point is going to have a architecture like this. You have a three-dimensional vector N, S, and A for these three, and then you have a three-dimensional P, corresponds to the X, Y, and Z coordinate of the location of the end effector in the three-dimensional space. So N, S, and A give you the rotation, and then this point right here, this point has the coordinates Px, Py, Pz. So again, when you look at two sets of values going from base to the third joint and from third to the sixth joint, you have these two you saw before. You can multiply them together and you get something like this. Now, what you have here, nx is equal to this row multiplied by this column. If I multiply this row by this column, this is going to be the one element of the result. One element of that matrix. One element is what? Is nx. So nx is this. If I multiply the second row by the first column, I get ny. I multiply the second row by the first column of the E2, I get this. And I can continue until I finish all potential multiplication of these two sets of rows and columns, and look what you get. You get 3, 6, 9, and 12 equations. That is this part of the matrix. That's 12 values on the right side. In the inverse kinematic framework, all the nx's and px's and a and sx's are available to you because you want to know where you want to end up, what configuration, what orientation, and what coordinate for my end effector. In other words, you need to know exactly where you are going to be right here. So you have those 12 values, you equate them to result of multiplication of these two matrices, and you get this kind of complicated problem. You know, you have C1, C2, 3, C4, 5, C cosine of theta 1, quantity multiplied by cosine of theta 2 plus theta 3, quantity multiplied by cosine of theta 4, cosine of theta 5, and so forth and so on. All of this is a tremendously complicated nonlinear equation. And you have to solve these 12 equations for only 6 unknowns. Theta 1 to theta 6. That's why it's so, it has infinite solutions. Some solutions are singular, where a location is not reachable, you cannot go there. So, back to the drawing board for the robot engineer. Okay? So, this is what's missing in our textbook. You see right here, this kind of complicated configuration. So I want you to basically do not just take something for granted in your own textbook by just going to the toolbox and do that. That's what I always tell my students, MATLAB is good, but not too good. You know, it addicts you to just getting some numbers out without appreciation of how that number came about, how that code was made, what are the theory behind it, on what foundation those commands were written. Okay. Now, if you remember from this table, if you remember this table right here, this table, for angle 90 and 0 and 90 and 0, 0, 0, you have these values. So, if we give those angles, if those angles 90, 0, 90, 0, 0, 0, we give it to the resulting t, it's going to come up to be like this. This is the configuration of Puma 560 in its base location, in home location. Home location is always have the robot going to the ceiling because that's the safest way. It will not harm anybody. Okay, it's all things like that. And you will be doing the same thing, hopefully, in your homework on ABB with the help of Ikram. You need to start with the robot in that location and then do your experiment. Okay? Maybe you can write your name with that Puma 560 program, you write your name. Okay? We'll see what the Ikram has in cooking for you. Okay. Now, let me go to the beginning of your textbook. If we, let's say, this is the introduction of the book. In fact, let me see. Here is the nomenclature I mentioned to you. You have to have it under your attention, so that if you run into something in the book, what is this? You go to the nomenclature. For example, this is the estimate of x, x hat, mean of x for relative value, direct value, a vector, norm, a scalar norm, transpose, pseudo-inverse. That's the inverse of a non-square matrix. We call it pseudo-inverse. And then, of course, you will come to some of the things that we already have possibly got. We have mass of a link. We have, we'll talk about quaternion later on. Homogeneous transformation, we have seen that already, T matrix. Homogeneous transformation representing frame B with respect to frame A, like this. Notice that the inverse of homogeneous transformation of B with respect to A is equal to the A respect to B. Okay? Or vice versa, A respect to B here, B respect to A here. So the homogeneous transformation are orthonormal matrices. Okay, that is a property which you need to know. And tau will be the torque, V will be velocity, X, Y, Z are Cartesian coordinates, and so forth and so on. Then it has a whole bunch of symbols like this, okay, which some will come into discussion later on. So the toolbox is something that I'm counting on you that you already downloaded on your computer. Okay, goes to the history of the robot, and you remember that George Dewar and Joseph Engelberger in 1956 they started the first robotic company, and they were both back in '54. Both of them were graduate students in physics in Columbia University. Mr. George Dewar passed away many years ago, and Dr. Engelberger, Joseph Engelberger, unfortunately passed on December 1st, 2015, at the age of 90. So here is a ABB robot. You're going to be working with this kind of robot. This is George Dewar, passed away in 2011, and of course, now they can unfortunately add 2015 here. Dr. Engelberger, actually, he didn't have a PhD. What he did have was honorary doctorate degree, like from Carnegie Mellon, for example. He got several. He's considered the father of robotics. Yet he didn't own the patent of the first robot. I mentioned to you, he purchased it. Okay? But he is such a kind person. He brought Mr. Dewar into the company, they did it together. Even though he could have said, okay, you know, I own the patent, see you later. Okay? So, and I remember I was honoring him in year 2000 in Maui. The whole conference was dedicated to Joe. And he was looking for $5 million of investment money to put a robot in every ward of hospital. Make all those orderlies in the hospital wards a robot. And the robot, unfortunately, was so expensive. A university hospital in Honolulu rented it from him. Put it in the hospital ward. And now, right here in UTL Science Center, they have a robot, which my students, including my former student, Dr. Patrick Benavides, we have gone there to try to help them put simultaneous localization and mapping on the robot to be more efficient in Florida. That robot goes to the downstairs in UT, and they load it up with they unload it with all the dirty clothing and material and other maybe towels and what have you, which collects in everywhere. Then it goes in automatically into the elevator, goes up each floor, makes its round, come back to the elevator, goes to the next one and next one. So now robot is becoming a lot more affordable than when late Dr. Engelberger was trying to sell the idea. But you see here, the Tonight Show, starring Johnny Carson, which was on TV before any of you were born, okay? And he took a Unimate robot to the show on NBC, poured a beer, potted a golf ball, and directed the band. It was done there. I have the video. I have to find it in my house. Joe gave it to me. It's now a museum item, okay? And I will convert it from VCR, VHS to a DVD, and hopefully I'll bring it. I'm going to make a effort this weekend to bring that Joe's, Tonight Show video. He gave it to me when we were honoring him at the conference, because he showed it at the banquet in his honor. So, and this is the important thing. He promoted robotics heavily in Japan, which led to a strong investment, development of robotic technology in that country, and gave testimony to Congress on the value of using automation in space. He has written 2 books on robotics in practice, robotics in service. So that's the issue. And now, of course, robots can be under the water, as you know. Everything can be programmed in any domain. We call it a robot now. Okay. So this is a NASA drone. Okay. And when I come back from Dubai on the 8th of February, I will bring my pictures from the drone, international drone competition. Show you all the drones coming from all corners of the world and who won and so forth and so on. It's a 3-day event. I doubt if something that big comes in. These are professional. These are manufactured. So let me, of course, you have seen the Mars rover, which is still on Mars, and the Japanese Honda Asimo humanoid robot. I don't know exactly how tall this is. It looks like it's not more than 1 meter. It's about 1 meter?
No, brother, it's 120.
1.2,
yes.
1.2 meter. The robot, we have, in a week we are going to order 2 humanoid robots for A-Slab. And one of them is 85 centimeters, which is about maybe about up to here. Okay. And the other one is just the torso, the upper body. We're going to put that on a mobile robot, and the other one walking. Okay. And Berat's group have already printed a lot of parts of it, even before we have ordered it. So hopefully when it comes from overseas, they're going to ready to cover it. Okay. So anyhow, as you can see, the robot is hands in hand with the code of toolbox. This is 3 of the commands. CTRAG is the Cartesian trajectory. When you want to move the robot, actually do something in real world, you need to have a trajectory to move, and that's that command. Here is a translational movement, when you want to move from A to B in one translation. Of course, plot is the original from matter. Okay, no big deal about that. So, all right, now let me see what we can do in terms of additional material. So, part 1 consists of 2 chapters, presentation, presenting position and orientation, chapter 2, time and motion, chapter 3. Some of the comments here are, what you see here is essentially, as you remember in the slideshow, that we showed how you move in one direction, in 2 directions, then you have, that gave birth to the concept of rotation matrix because of those cosine and sine relationships. Remember that? That's what that is. That's what that is. Then of course, you have this command here for composition, which is in the nomenclature. So you run into that, you go to the nomenclature. And here, for example, you have a point P here, which is describe the coordinate relative A, B, and C. So it is A looking like this, and C looking like this, and then B would look like this, which doesn't show it here. So you have all of that. And then to reach There you can do from here to here, or you can go directly to here. So this whole idea is the fact that when you move from base to the end effector, the coordinates are all have a transformation matrix among each of them. First to second, second to third, third to fourth, and so on. Okay. Now, in 2-dimension, you saw this already, that you could have a rotation along the axis X coming out of the page, and then you have an X and Y coordinate of the coordinate of the new vector, and the P has two representations, AP and BP. The same point, but has two different coordinates in two different coordinate systems. And they look like this, Vx and Vy, with respect to B, it looks like this, and with respect to P, it looks like that. Okay, so finally you get a 2x2 rotation matrix, as you see here. Call it V, R of vector V with respect to coordinate B. Okay, let's see what else is worth mentioning. And of course, if you want to do all this rotation, you can do that by doing this kind of. You can define your axis, 0, 5 here, 0, 5 there. You can have plot T1 on frame in color blue, which is this one, and so forth and so on. We'll get to that. You know, as I said, I'm going to give you a little bit of introduction into the toolbox today, and hopefully on the 16th of the month, Bharat will give you a complete lecture on the toolbox, on toolboxes. And in the meantime, between your homework 1 and then, I may give you a pencil and paper homework to do some of these things by hand, like doing forward kinematic of tooling robot, or inverse kinematic of a tooling robot. Use your mathematics. Okay. And then you can repeat that homework on the toolbox. What I hope that what I'm asking Bharat to do is to actually take you into a sort of a complete tour of the toolbox in the following sense. It defines links, defines joints, then defines the robot. Okay, it has already built-in robots already. Puma is already there. Tooling is already there. ABB is not there, but I'm sure maybe Stanford is also there. It's already there. So then he takes you to forward kinematics. He demonstrates inverse kinematic. Then with some joint trajectories, some Cartesian trajectories. Okay, and then eventually you have the whole robot move into a space. You control it. You simulate the whole. Okay, and that means I need to show you, and I'll do it today, dynamic behavior of the robot. Remember kinematic, what did it say about kinematic? Is the relative position of these links regardless of how the motion was created. Now, in the chapter 3 of Hu's book, and chapter, I think, 9 of your book, it talks about the dynamic model of the robot. And it is based on two sets of mathematical equations. First one is Newton-Euler, two legends, giants. The other one is Newton-Lagrange. Okay? And if you pay attention to the file and the report I gave you for the tooling inverted pendulum in your homework plan. If you read that section, the one I told you to read, it is Newton-Euler is there, right there, which is the partial differential equation of the total energy of the robot, of any mechanical system. Of course, Lagrange didn't even dream of what robot is at the time, but they did it, fundamental work on a chain of mechanical devices connected together. Okay. So, let me see what is, this is the right-hand rule I mentioned to you. You have one product with the second rule, the third one will be coming the other direction. All right. Orthonormal rotation matrix. Rotation matrix is orthonormal, which basically means that the robot looks like this, and the transpose of the robot is equal to the inverse of the robot, right here. That's the definition of orthonormal matrix. Okay, when a matrix inverse is equal to its own transpose, it's an orthonormal matrix. This comes from linear algebra. So, again, you have this kind of plot. For example, if you want to rotate along the x-axis, pi over 2, you get this R matrix, rotation. And you multiply by a rotation along the y, also at pi over 2, multiply together, you get this. Okay. This is, of course, history behind Euler. You can read it. You see, you have been hearing these names quite a bit for your whole education. You know, you learn some of them in control courses, some of them you have learned it in signals and systems course, you know, in mathematics. Now you know where the origin of those names are. Okay. Okay, so let's say you have a rotation along the z-axis of phi angle, a rotation along the y-axis of theta, rotation along the z-axis of zeta. This could be pitch, yaw, and roll. This is from the end of the link 4 to the tip of the robot. You have those three rotational matrices. And this final value R gives you NX, this is NX, AX, and AX. Those three matrices that you saw in the other chapter equating those 12 equations. Remember? Of course, you also have a PX, PY, PZ here. All right, let's see. Singularities and gimbal lock. This is singularities are when the robot gives you a solution which is impossible to achieve. Okay, you have one location you want to go, but the location is not reachable. You cannot do it. Okay, you cannot do it. Then that's a singular solution for the inverse kinematic. Okay, so and gimbal lock is something which is a device that you have. You see here in figure 2.13, and in Apollo lunar module in Apollo 13 where we had problem and there's a movie was made on it. One of the issues was the gimbal was close to being locked and they couldn't open things to land. Okay, that was the problem, or one of the problems. So let me stop and let's take a regular break. That means stretch your legs.